Sorry, I'm having trouble with my mouse now. Sorry for this. It's just a problem sharing the system, presumably coming back up. Can you see that slide?
Yes.
Okay, so the question I was asking before we were interrupted by failure of technology, if this experiment was set up to change the depth of the high rate pond. So if you were looking at an algal culture that was in the same in a vessel, same surface area, so it's got the same interception area for sunlight to shine on the pond, and you increase the depth or decrease the depth, how might you expect the algae to respond when you did that?
Well, by decreasing the depth, we expect to have more biomass of microalgae.
Yeah, that's all I'm after, really, is you'd expect if you increase the depth into the same conditions, you might say, well, okay, we're going to get less algal production because the light climate within the culture, the light being intercepted by the algae scattering, all the geometry of the vessel changes in terms of light availability for the algae. So this is an experiment to see if you do that for wastewater treatment and you're relying on algae for wastewater treatment, by changing the depth, do you change the outcome of the treatment? Does it really change the treatment? And this was done between May and March, long period of time, because we're trying to make sure we're doing it in the same season. So it's a comparison. What we did here was we did this comparison in South Australia. With climate change, we found it difficult to try and do it by season, to say, oh, we want to do spring, summer, autumn, winter, because there's not that big a difference. So what we did, we ran these ponds in different seasons, but we divided the seasonal data, which I'm going to show you. We divided the seasons into, we worked out that the average temperature was about, at the time we did this, was about 17.5 degrees. And we said anything above 17.5 is, in inverted commas, warm, and anything below is the cold season. And we tried to operate these two pond systems at the warmer period and the colder period so we can understand how they behave. But what I'm showing you here is if we did this and then we looked at the retention time changing, and then we looked at the effective depth and season on that, what actually happened. So this is some interesting data from where we were talking about the depth. So the deep pond is the 55. So what we've got here is different parameters. So this is the fraction being removed from the inlet value of BOD. This is the fraction of the inlet phosphorus being removed. This is the fraction of, sorry, that's the fraction of nitrogen. This is the fraction of the phosphorus. This is the log reduction values. I talked about that before. So this is the amount of E. coli, the difference between the amount of E. coli coming into the high rate pond and the amount of E. coli going out of the high rate pond, what's been removed in terms of log differences. And then what we've got here, I don't know if you've ever seen these plots. These are what's called violin plots. And there is a form of box and whisker plot, but what they do is they give you a more graphical presentation of where the bulk of the measurements are. So the fat parts here are where a lot of the measurements were in the similar range. Where fewer measurements are here, there was only 1 or 2 measurements here. It gives you the median of the individual violin plot, and it gives you the mean of the individual violin plot. And then this line gives you the overall mean of all the data for that particular parameter. Okay. Okay with that? So what we were trying to do here is show that there was a lot of data collected over this period, and it was quite a robust data set. And the x-axis, pretty hard to try and get all the description, but what we've got here is all this data here is when the ponds were operated at temperatures less than 17 degrees. And this is when the ponds were operated at temperatures greater than 17 degrees. So the data for temperatures greater than 17 degrees, temperatures lesser than 70 degrees centigrade. So, and we've got the deep pond, that's when it was 55. This is when it was about 40, 43. And this is when the shallow pond, when it was 32. So deep to shallow, warm, cold. That's the way they're all organized. So this is just looking at BOD removal. And one of the points we looked at was we could say, okay, overall, there was very little difference on the treatment to remove BOD by changing depth, because the median values were all much the same. The median values of the data within these violin plots were much the same. The only case was maybe in a deep pond, when it was cold, the removal was slightly less. But we're talking here the difference between 90% and 95%. So it's marginal, but it might be considered lower. Similarly, when you look at phosphorus removal, again, the cold in the cold when it was less than 17, I'm resisting the temptation to say winter, but in a cold pond system, the deep pond probably led to lower phosphorus removal. But again, in the warmer periods, it probably was marginal whether there was any effect. Statistically, there was no effect of phosphorus. It was only in the cooler periods you might argue that you would operate shallow ponds maybe, but there was no, it wasn't as if the shallow pond at 0.3 really outperformed the 0.4. So quite interesting whether there's actually a linear relationship. Doesn't look like it. The one that was consistent was there would be an argument that if you wanted better nitrogen removal in the cooler seasons, cooler months of the year, you might operate a shallow pond for better. Oh, why did that happen? You might operate a shallower pond for better nitrogen removal, because in the winter, in the cold periods, less than 17 degrees, a deep pond only removed about 25-30% of the nitrogen, whereas up here we're much higher. But again, in the summer, it didn't much look like there was any difference between depth of operation within the above 17 degrees. Didn't seem to make much difference. And overall, this was one that was really quite an interesting result. Overall, for disinfection and E. coli removal, it looked like there was no difference, no temperature difference, and no depth difference that affected E. coli removal. So we were getting about 1.5, 1.75 log removals, and we were over 2 in the warmer periods if you operated as a medium depth pond, but probably not a lot of difference. And that was an interesting result because we think that the shallow depth and the biomass that we were operating at, there was probably, even in the cooler months when you have less sunlight, shorter day length, there was probably still enough UV to affect disinfection on the residence times being applied. And of course, one of the interesting things here is that, and this is something that's quite, I think, quite an interesting question, is this was displayed on depth because that's what, as I'm a phycologist. I did my PhD on algae in freshwater lakes in Scotland. So I was again thinking about depth and light and algal photosynthesis and algal growth. But in actual fact, you could equally plot this as change in retention time, because the deep pond always has a higher retention time. So these are all, the deep ponds all have the same retention time as well as depth. It doesn't change it much, but it may be we're assigning depth, whereas it could be retention time as the factor, possibly more likely that. Any questions on this?
No.
So one of the experiments that we've got some data, I think, but we've never published it, is, it's the control parameter for a high rate pond, or for any pond really, is, when you get into, I don't know how much I know Jeremy was when I spoke last, Pierre was in the room, and he was talking about Jeremy introducing you to photobioreactor design, etc. And one of the things when you're operating a photobioreactor and you're intentionally growing, say, a single strain of algae for producing biomass for some purpose, one of the parameters you can change is dilution rate. Dilution rate is the same as retention time. It's the rate at which you add liquid to your system. With a wastewater treatment system, you can't change. If you've got a constant area pond, you want to operate it at the same depth, you've always got a constant flow of wastewater. The community is always producing pretty much the same volume of wastewater on a daily basis. So I'd say things are pretty near uniform at 12,000 litres a day. Occasionally it goes up to 16,000, but generally it's 12,000 litres a day. You cannot ask people to stop using the toilet and to reduce the number of showers to change your retention time. One of the few controlling parameters you have is depth of operation. And that's been a question for a number of years. Is there any advantage? What we're asking here really is there any advantage in treatment performance terms to changing the depth at different times of the year? So is there an argument for saying, I want to operate shallower ponds when it's less than 17 degrees, when the weather is cooler? Do I change the depth to maintain treatment? In the summer, can I operate deeper ponds because the light intensities are higher? I might get higher rates of algal photosynthesis. Can I change the depth? Will that give me any advantage? And overall, I think the data, apart from nitrogen, the data here overall shows there's probably little advantage to changing your depth and having all the added complication of changing the depth of a very large pond. Engineering depth changes. We could do this quite easily, but took a lot of the engineering design is quite novel about how we do this. But designing and having an operational manual that says change the depth of the pond. In our case, winter would be July. Change the depth of the pond in July and operating at 0.32 meters deep. Is there advantage to that for a very short period of time? To complicate operation? Probably not, in my view. So we tend to operate constant depth ponds. Is that okay? Is that clear? Would you argue with that from these data? Is the interpretation right? Again, this was published in Algal Research. Okay, I'll move on. Okay, so here we are now. You'll note here that this is the first time I've talked about suspended solids. And I've called it suspended solids because of the photomicrographs, the images I showed you of how algae grow in wastewater ponds, in high rate ponds. They are not pure cultures of algae. They have algae, they have bacteria, they will have some protozoa because the algae and the bacteria are food for other organisms, and they'll occur in your wastewater and they'll come in on duck's feet just as much as anything else. So you have algae, bacteria, protozoa, zooplankton. You'll also have solid material that the bacteria can't degrade. And when you do your classic solids measurement, where you take your wastewater, you filter it through a dried weighed filter pad, you then dry the filter pad again, you weigh the filter pad, and you measure the difference between the initial weight and the weight plus the filtrate gives you the suspended solids. This is a productivity that you might have seen already, or you might be familiar with in terms of, we often talk about aerial productivity of algae in terms of grams per meter squared per day. So these are the values that we got in this experiment for that mix of algae, bacteria, zooplankton, detritus, the unbroken down material. So this is what you'd get as solids out of the pond that you might consider algal productivity, but I resist calling it algal productivity. So the solids, as you'd expect in the cooler period of time, the productivity is relatively low. But we're talking here about 0 to 50 grams per meter squared per day. And when you get into, sometimes you get very high productivities, maybe an aberration, not quite sure why that happened, but it was consistent where we got a very high productivity for a very short period of time. Gain here, few high data points. They may be outliers because of dense mats of algae being included in the measurement, not dispersed algae. But basically, these are very high productivities. If you just look at this axis, we're talking here, the mean productivity, when we looked at the whole value here, it's about 22 grams per meter squared per day. And that is, in terms, if you compared that with an algal productivity, and we're not saying this is all algae, but the dry matter and what you could use this dry matter for say, producing energy from various means we've talked about before, like anaerobic digestion, hydrocarbon liquefaction, etc. These are the biosolids that will be available to get energy out of, for instance. These are some of the most productive dry matter systems on the planet. That's not an exaggeration. These systems are producing more dry matter in grams per hectare or grams per meter square per day than sugarcane is in Australia. They are very, very productive. And if you compared these, when you look at some of the systems where, you'll be looking at papers where people are trying to grow isochrysis and nanochloropsis in marine waters limited for nitrogen to increase the fatty acid content, you'll find their productivities are easily a quarter of these. They may only be 5, 10 grams per meter squared per day in really optimum conditions as single cultures, provided with CO2 added under pH control, etc. These systems, in terms of biomass production, are enormously productive. And one of the things we're interested in working, we do research with JPA and Jeremy and Mariana. One of the things we're interested in is how we can produce value. What can we do with this biomass to produce value-added products from biomass grown on wastewater, part of the circular economy? How can we add value to this? Because they are very productive systems. And I'll talk about that later. Again, there is some influence of depth, but currently we're more interested in wastewater treatment than we are about biomass productivity. But they are productive, take-home message.
But in this these suspended solids, We have
Yep.
only, how can I say it? It's not only for microalgae, it's for other bacteria or microorganisms that are there. So for this circle economy, it's more like a purification of these
Well,
suspended solids. Or
yeah, good question. I mean, I the evidence from other research is you can't economically treat wastewater in a photobioreactor by inoculating with a defined algal strain, because you can't keep that. You will always have algae come in the wastewater, and you can't keep that monoculture of algae. It's expensive to run. Capital cost is enormous. So photobioreactor design either closed high rate ponds with sealed high rate ponds. In my view, you're going to find it very, very difficult to have a controlled algal production system using a single monoculture. So you have to accept the limitation. And the question is, and it's a question for you guys. I mean, it's a research question. You can see my image. I'm at the wrong end of my career, having done this for 40 years. The question that Jeremy and I and Guillaume and Mariana are posing is, what can you do with this sort of biomass that's a mixed biomass with algae, bacteria, everything else? Mostly algae. I mean, it is mostly algae, but not entirely algae. It's not what I would call the sexy algae, like Nanochloropsis, Isochrysis, all the things you can get, Dunelliella for pigments. It's none of those. It's Chlorella and Chistrodesmus. It's the boring weeds of the algal world. But when I talk about the bigger pond system we operate, we would get 72 tons out of that algal system that exists in South Australia already. The question is there any product that is worth putting in a system to remove these suspended solids and work with them to produce something of value? Because where I came in, we were talking about, using wastewater as a nutrient source to grow algae. Well, we're already doing this. This isn't now, in my view, and I hope I can convince you when we finish this lecture, which may be next time, but I'm hoping I can convince you that this is already on the ground in South Australia. There are already high-rate algal pond systems operating in Spain. The question is it worth, do you just see them as wastewater treatment systems? Because wastewater, as we move into climate change and water scarcity, water security becomes an issue. In the European Union now, there is increased interest in wastewater recycling, that is using the wastewater intentionally for agricultural production. So is it worth, do you just take the wastewater as being the product of an algal-driven wastewater treatment system? Or can you take the product both as wastewater and the biosolids that did the wastewater treatment for you? Can you value add in the circular economy by using those solids for beneficial use? In Spain, they've demonstrated you can produce, you can put the biosolids from a wastewater treatment system that's predominantly algae, you can put into an anaerobic digestion, you can gain the methane, you can compress the gas, put it into bottles, and you can drive cars on it. So there's a water utility in Spain using high-rate algal ponds, taking the biosolids into an anaerobic digester, producing methane, putting it in bottles, and then demonstrating that you can use that methane to run a vehicle fleet. It's probably not going to be, in my view, you're not going to do that on a commercial scale. You'd need very large areas to produce significant quantities of biogas, but it's good to demonstrate that you can do those things. You could equally do it static anaerobic digestion of biosolids and produce methane to generate electricity to run your high rate pond. You could do that. But are there other things that could be done? That's a research question for you guys. How do you incorporate biosolids production, predominantly algae, but not exclusively algae, and wastewater treatment, and get the benefit of both the wastewater and the biosolids? Yeah.
Yes, sure.
An exciting question, or maybe not. So when we got to the end of this, I mean, I've only shown you the comparison with the facultative pond and not the maturation pond. And in actual fact, what we showed was that the benefit was of using a high rate pond. So what we showed was there was no difference. I mean, the big difference was retention time. So the retention time, only 5 days in the high rate pond, 30 days in the waste sterilization pond. We had the same degree of treatment with a pond that was much, much smaller, equivalent for the equivalent volume treated. It would have been a much smaller pond. We got the same disinfection between the system. We got the same phosphorus removal in the system. We showed that the depth of operation of the high rate pond had little effect on the treatment performance. We then started to look at the surface area requirements. So the high rate pond would require, for the same volume of effluent being treated at a 5-day residence time, it would be half the size of a pond easily. The shorter residence time means there's lower evaporative losses. So there's more water available for reuse using a high rate pond compared to the waste sterilization pond at a much larger hydraulic retention time. So there's almost twice as much effluent available for beneficial reuse. So the conclusion of the study was that high rate algal ponds are a viable alternative to waste sterilization ponds for use in South Australia and in similar climates. The comparison, when we looked at why I'm saying the facultative pond used in the high rate pond for the whole treatment was shown, was because the performance of the high rate pond was actually better on the strong septic tank effluent, the more concentrated effluent, than if we treated the effluent that had already been through a facultative pond and we were trying to replace the maturation ponds. We showed that it's much better if you take the septic tank directly into the high rate pond, and it will produce equivalent treatment performance. Phosphorus removal, I think that's another research area that needs to be really investigated. I think we oversell phosphorus removal in algal systems, but that's another research question which we can talk about later. Inorganic nitrogen removal was inversely related to depth in the colder months, but independent of depth in the warmer months. And the recommendation was we'd operate the pond at about 0.3 meter deep in the conditions prevailing in our Mediterranean climate, was the conclusion of the study. So I know I'm going to finish early, but I think it's probably good just to leave it for the next lecture to pick it up at the end of these conclusions. I don't know. Mariana's not in the room, so maybe she'll let me do it because she's not in the room. I'm quite happy. Have you got any questions of what I've been talking about tonight so far, or your morning, my evening? It's 8:30 in the evening here with me. Have you got any questions, comments?
Yeah, probably this using microalgae for this wastewater treatment is still being studied, isn't it?
Oh yeah. Well, I would say I was at a conference this year in Portugal, and we ran a workshop. It was the applied phycology symposium that was held in Porto. And the group from the leader of the group from Spain was there as well. and a leader of the same looking at high rate ponds in the US was there. We ran a workshop, and the workshop was based on the question of why haven't these systems been more exploited? Why aren't there more systems? Because my view and the view of the group in Spain that have done the same sort of research is that these systems now are ready for implementation. And I'll talk about the energy demand later in the next lecture. But these systems, they are not. I'm being honest here. When I read papers where people talk about the potential benefit of using algae for wastewater treatment, my response to that is we're already doing it. Kingston on Murray, high rate pond, is treating the effluent from 300 people. And it's treating the effluent to an acceptable standard by the health authorities, which I'll talk about in the next meeting. But the technology, I believe, has come of age. It's not something, as in its current format, it's an acceptable wastewater treatment system. And really, part of it is to do with engineers. Are there any engineers in the room? Part of it is to do with consultant engineers who are they are used to more highly engineered systems, and from their point of view, there is actually more economic value to them in putting in highly engineered systems. So a consultant engineer, a consulting company who is doing a design for a wastewater treatment system will actually gain more income by putting in pumps, blowers to blow oxygen or air into the system. The more complex the system, the more money they make. So they may make between 10, 20% on the installed items of equipment. There's an economic benefit to installing complex systems. The disadvantage, of course, is the capital cost goes up for the user and the operating cost in energy terms goes up as well. So you actually start to burden communities with excess capital costs and excess operating costs. And it's an argument that we have to win, but we have to win it not as phycologists, in my view, not talking about algae. We're talking about wastewater treatment for benefit to public health and at a cost that communities can afford. The challenge then is to say, okay, if we move on with the circular economy, then what can we do with the biosolids from these systems? What can we do that adds value and recoups some of the cost of operation? So I think, there's refinements that can be made, but in essence, the research that has already been done has demonstrated that they are systems that have come of age. They have transitioned from research to adoption, is my argument.
Okay.
But notwithstanding that, I would say, I think Jeremy's going to start talking about this. We've had one of your previous student on the program has just done a joint PhD with Jeremy and myself. So they spent 2 years in Nantes and they came to South Australia for a year and they worked on the existing pond systems. And what we're looking at is the microbial ecology. We're trying to better understand how these systems work. And through that understanding, we may be able to improve their performance and make them even more efficient. So there are research questions from the point of view of how algae grow in these systems, how they interact with bacteria in these systems. We're working, I'll talk a bit about it in a subsequent lecture, we're working on new operational strategies for these systems to improve performance. But as they currently stand, they are still competitive as functional wastewater treatment systems for communities that currently don't have wastewater treatment systems.
Mm-hmm. Okay.
Okay.
Okay. Yes, that answered me.
So I'm trying to encourage you to think about research questions. We're keen to continue the research. Okay, I'm going to leave it there, and I'll pick it up next time, and we'll talk a bit more about how we've further transitioned to adoption of these systems. And I think that's Friday we meet. Yeah.
I'm not sure, but I guess so.
Yeah. So
Excuse me.
thanks for getting up early and starting at 8 o'clock.
Excuse me, sir.
Made my life a bit easier.
Before
Okay.
that, could you please send those slides of the previous classes and today's, so that I think it would be better to prepare to us when we have next class.
Yeah, I should have sent them on to Mariana. I'll send them on by PDF for Mariana to circulate, both these and the previous lectures. I apologize for that, but I'll do that. Make sure you get them, and then you've got these slides, and I'll send the slides of the next lecture as well, so you've got them all. Is that okay?
Okay, thank you.
Okay. So have a good rest of day, and thank you for attending. Bye.
Thank you. Have a good day.
Bye.